over a minute. That's one of the things we've been trying to get to is what's the path that we were kind of at tier L2. What do we need to do to get to a breadboard level of maturity where we can start looking at what do we need to harden for space applications? What do we need to do for some kind of on-orbit test? And so the last several weeks have been very encouraging for us with working in the gigahertz regime. So we just finished some work there. And we're also talking to Skunkworks as a device as well. They've asked us to take a look at. We'll continue to dialogue with them. Now, in terms of the, I'm going to jump over this in the interest of time. In terms of the value proposition of, say, 0.4 newtons per kilowatt, what does that mean from human spaceflight perspective? As part of my day job, I do human space exploration architectures for a living, so I'm working with how do we use Hall thrusters, how do we use chemical propulsion if we want to assist translunar space. Very familiar with all that stuff. So I had some, I had one of my interns over the summer, Ujra go through and do a whole bunch of mission analysis using Copernicus with some Q thrusters running between 0.4 newtons per kilowatt and all the way up to 4 newtons per kilowatt. And so this is a 90-ton spacecraft, so it's analogous to a single heavy lift. And out of that 90 tons, 50 tons is going to be cargo, 20 tons would be power. So at 10 kilograms per kilowatt, this is about like a 2 megawatt fission reactor. And then, of course, 2 megawatts of Q thrusters. So you build maybe 10,000 of one of the test articles that you saw, right, just in bolt them to a board. In terms of looking at going to Mars, you kind of see the 0.4 newtons per kilowatt really can help reduce the transit time to Mars. We're looking at 66 days outbound with a 70-day stay and 110 days back. Now this is not, the return trip was not optimized. We just set the stay time at 70. If you wanted to optimize the return time, it might stay on the surface a little longer. If we go to 4 newtons per kilowatt, you actually, with that very high thrust to power ratio, now this is still an in-space propulsion system. This is not something you'd use on the ground, but at 4 newtons per kilowatt, an in-space propulsion system is very, very useful. And you can kind of see when Copernicus optimizes the solutions, it can really get to Mars fairly quickly and back, even with a 90-day stay. You've got a lot more latitude in terms of when you leave. Now, looking at this same spacecraft to try and articulate the value proposition for those same figures of merit, here you're looking at a mission to Jupiter. We can get, and these are all captured, these are not flybys, so you accelerate and decelerate halfway. 194 days to Jupiter with a 90-ton spacecraft. So basically, with 0.4 newtons per kilowatt, we potentially have the capabilities we've typically looked at with the Array 5.0 for Mars transit times. Maybe we could do some kind of a Jupiter mission. Now, 4 newtons per kilowatt, you're starting to see a difference between the two. That's 61 days. Saturn, 0.4 newtons per kilowatt, is just starting to get beyond the 200-day mark. And of course, continuing on throughout the solar system, you see the transit times here, all the way out to Pluto. So at 0.4 newtons per kilowatt, it's just under 2 years to get to Pluto, and 4 newtons per kilowatts, starting to get close to that 200-day mark again. Now we did want to look at the 1000 AU for folks familiar with the literature. 1 tau is kind of a JPL interstellar precursor mission that they came up with in the literature. And so we wanted to go through and take a look, how could we potentially accomplish a 1 tau mission. So again, this is still the 90-ton spacecraft. We could get out to 1 tau in around 5.6 years with a 0.4 newtons per kilowatt. Now remember, Voyager is at 120 AU, and it took it 30 some odd years to get there. So that's potentially a pretty handy improvement. And at 4 newtons per kilowatt, again, you're really starting to see the difference between the performance. Now, it turns out that Copernicus can actually do interstellar trajectories. Dr. Cesar Campo, the guy that wrote it, put in the ability to put in galactic coordinates. We originally were going through and doing the rotation from galactic coordinates into what we thought Copernicus needed. But Dr. Campo is at JSC for sabbatical, and he sat down with us and looked through all these trajectories. And when we got to what we were doing on the interstellars, he told us, you don't need to do that, you can just put the values directly in. And so here you see so I guess all I had to say, Copernicus can actually do an interstellar trajectory. Interesting, I didn't know that it could. So 0.4 newtons per kilowatt, we're looking at a journey from here to Alpha Centauri, which is kind of orthogonal to the solar ecliptic if you were to look at a road map, so to speak. So that's why you see the trajectory kind of going very much out of plane here. It would take just a little over a century, and these are capture trajectories, so you're accelerating and then decelerating. So 0.4 newtons per kilowatt is exceedingly interesting for even interstellar flight. And then the 4 is there, but that doesn't have relativistic corrections because we get to, I think, just under or right at 0.2 C. So we'd want to redo that analysis with that in mind. So Now let me finish with this kind of a life imitating art thing. This is some artwork that was done by Matthew Jeffries back in the 60s. And Matthew Jeffries was the guy that kind of came up with the familiar sombrero look of the Enterprise that we all know. And he also came up with another version that kind of has this ring. And you can see that the ring ship kind of has some characteristics similar to what we talked about at the beginning of the talk that's in the paper published by Cuvier. Now this was done in the 60s, so it's interesting to know that an artist did this without any knowledge of what something like this might need to look like. We've got a few things pretty close to correct, but there's a few things that would need to be changed, right? The rings are too thin, right, based on some of the stuff I talked to you guys about. But then the other thing is that these two rings would generate a kind of like a little hemispherical dome here as part of the front part of the warp bubble, so it would kind of look like a hot dog. So when Kirk told Scotty to engage the warp drive, the bubble would cut the bridge off the spacecraft and it would float away, and Scotty would be in a lot of trouble. So I worked with the folks from the CBS and so forth to try and update this as a matter of kind of like an education outreach type of thought process to help people get excited about math and science. And so we worked together to update that artwork, and this is the Mark Rademacher is the gentleman that took the original artwork from Matthew Jeffries, and that previous nice picture was done by Mark Rademacher. So I worked with Mike Akuta and Mark Rademacher to factor in some of the changes based on the physics. And so you see the spacecraft has much more athletic-looking warp rings. They're much thicker aspect ratio. The spacecraft fills more of the volume. If you're going to go to all the trouble to make the bubble that big in diameter, you're going to fill it with everything you can. So it's not going to be dainty-looking like the previous one. And then the spacecraft is going to be within the bubble itself. You wouldn't want any part of where the crew is to extend out into the fanning region, because that might, some poor crew member might be walking through a hallway and unfortunate. So, okay, I think that's enough for now.
Yeah, we're out of time.
Yeah. So, thanks.